look at quickly exports and then look at quickly the nuclear reactor example. So basically, you have a solid tube with uniform generation, and the outside is actually insulated, but there's a limit to the temperature of the surface. Basically, it's the TS2. That's the limit, and the tube is actually cooled at the inner surface by cold fluid, by coolant here, with temperature T infinity and with heat convection coefficient H. So basically, heat will be taken away from inside. This is the case slightly different from the cylinder case just talking about. This it's cooled inside, not out surface, but inner surface. And actually, how to solve this problem is actually quite similar to the cylinder problem. It's just have different boundary conditions now in this case. Different boundary conditions. Now you have, say, for the inner surface, you have that convection, typical convection boundary condition, and the outer surface now you have insulated outer surface. So let's look at that. The heat equation is still the same because now you apply that heat equation for the cylinder. It's the same equation, and then you have the solution. General solution is still the same as well, but you have different boundary conditions now. The boundary condition is that first of all that the outer surface temperature, that's the limit. The outer surface temperature T surface 2, and also that if it's insulated, then you have, say, that's insulation boundary condition, and then you can actually find out that further, say, you have that temperature distribution expressed as TS2, but then now TS2 is not given, so you can try to find out, say, the maximum temperature, what maximum temperature could be, actually. So you have now the temperature distribution. Actually, that's the temperature distribution within that cylinder, with outer surface actually insulated, and which has temperature limit, that's TS2. And then you can then, from that, you can then try to find out heat removal rate by using that, once you have that say, temperature division, you can then find out heat removal rate or heat transfer rate. Basically, at say the inner surface R1, then you can have say that's the, so we actually try to obtain that heat transfer rate per unit length of the material cylinder. So it's QR over L. Basically, that's the total surface area, the inner surface area, and then the temperature gradient at the inner surface. And then you can find out that heat transfer rate can be, say, found to be like that. So if you have Q dot that much heat generated in the cylinder, you need to say that's the heat rate per mass, unit mass, to remove that much heat and to make sure that the temperature of our surface temperature is less than TS2. This is actually the minimum heat transfer rate required per unit mass to actually maintain the temperature. Apparently, it's the fast or the more heat is removed by the fluid, the lower the temperature, our surface temperature. And also, you could say find out that the heat transfer rate by applying heat balance over the whole, say, the tube. Okay. But basically, say over the whole tube, the heat generated equals heat transfer. So basically, you can then quite easily say, you just find out how much heat is actually generated inside the cylinder, this, and then you can find out that that's how much heat you need to remove. And to find out the per unit length, the heat rate per unit length, you just divide that value by the length, so which is this one. Okay, so also then if you say further apply energy balance to the inner surface, basically you know that the conduction, because on the inner surface, heat conducted to the surface should equal the heat convected or heat transfer by convection. And so you can then have that this is heat convection, and this is heat conduction. Basically is obtained by using Fourier's law, basically minus K A dt by the R as R equal to R1, and which is this value. And then is that. Then you can find out the heat transfer. So that's the heat convection coefficient to require to actually maintain the temperature, maximum temperature of our surface to be less than this too. And basically, apparently, as you can see that this is to maintain the maximum temperature to be less than PS2. You need either increase the heat convection coefficient, because you want to maintain that to be cool. So you need to actually increase the heat transfer rate. That's the convection coefficient, or increase the heat convection coefficient, or you actually have less heat generation. Basically, this one shows the result of maximum tube temperature as a function of convection coefficient as well as the heat generation rate. Basically, you can see that you can imagine that as when you have higher convection coefficient, the maximum temperature will be lower. Similarly, when the heat generation rate is smaller, then the maximum temperature will be smaller. Okay, so I think that's about the heat conduction with heat generation. So the only difference is that now you have one more term in the heat equation, and all the rest will be the same. And then you solve that heat equation and use the boundary conditions to actually obtain a special solution to get the constants. And then you have that temperature distribution. With that temperature distribution, you can then find out heat transfer rate at any point by using Fourier's law. That's how heat conduction problem is solved. So that's it. So the quiz will cover here today. So we'll cover basically heat conduction, convection, radiation, and general equations, and also one-dimensional state conduction problem without interaction. You should be able to actually particularly you should be able to identify heat transfer modes, and you have clear idea. So you understand the concept of conduction, convection, radiation, and you know the basic equations. And also you should be able to actually draw, if you can identify heat transfer modes, you should be able to draw the modes as well, how they should be in the direction of that sort of thing. And also you should be able to, for one-dimensional state problem, you should be able to draw that a thermal circuit, so that you could solve commutative problem. So you should be able to use the concept of thermal resistance to solve problem quickly, to solve one-dimensional state without generation problem. equation for typical one-dimensional steady-state problem, either with or without integration. And you should be able to also write boundary conditions. Okay, for a problem given to you, you can identify the function laws on substitutes and then write boundary conditions correctly. You will not be required to actually solve the equations on the equation, but you should be able to write the equations. Yes, any questions so far? We will have the tutorial session next Wednesday. So basically, you should use that time. Yeah, and then the quiz will be next Saturday. Yeah.